Rebecca.
I don't have, you have like the official.
Yeah, so
This is all the official stuff, yes.
You can hold on.
All right, so I think we can get started. It's my pleasure to introduce Ramon Iglesias. He's been a PhD student in my lab for a few years now. And I think he's one of the best examples about how to enjoy your life as a graduate student.
I don't know if it's a compliment.
Every time I email him, he was either in some birthday party in Colombia, or hiking in Japan, or venturing somewhere in the world. So you should learn from him how to concise work. But in between trips, he delivers some very good work on the topic of autonomous mobility on demand, so how to manage fleet of vehicles, in particular autonomous vehicles, in the context of a futuristic society, whereby we have companies like Uber managing large fleets of autonomous vehicles. When he started the PhD in my group, this was still perceived as a fairly futuristic topic. Now, of course, it's a very hot topic. So, of course, Ramon was in very high demand in his job hunting period. So I'm very happy about it. And Ramon analyzed these systems both from a theoretical standpoint, but remarkably also from a practical standpoint. In particular, some of these algorithms have been deployed in the field in Japan and have been used by Toyota to manage the system that Toyota manages in Japan, such a system called AMOD. So Ramon will tell all about this. I'm very excited to hear about his defense.
Thank you, Marco. And thank you all for being here. As Marco said, I'll be talking to you about how to coordinate this futuristic large fleets of autonomous vehicles from a modeling and from a control perspective. And if this is connected, it will work.
I hope you didn't forget the receiver in Colombia.
No. I might have forgotten other things in Colombia. So we all know, either by news or by seeing them, that self-driving cars are just around the corner. You can rarely go a day in San Francisco without seeing a Cruise or Zoox car in testing. And it is not an overstatement to say that this is a transformational technology. Whether it is by returning the time that we used to spend behind the wheel, or by removing the human factor in travel and creating this transportation system much more safe. Autonomous vehicles promise to deliver a lot of benefits for society. That's one of the paradigms that is shaking the transportation industry right now. The other one, and the one that we might be much more familiar with, is the area of mobility on demand, where a customer can just request or summon or reserve a vehicle with the thumb of his hand on the phone. And then he can use that vehicle to go wherever he wants. We've seen this to take over the world, all over the place, whether Grab in Asia, Uber and Lyft here in the United States, or Didi in China. But the real combo is when you combine these two paradigms. When you combine the idea of mobility on demand with vehicles that don't need to be driven by a human, you enable a whole new breadth of possibilities. Let me give you an example. One of the biggest issues that we face in these mobility on demand systems is that vehicles tend to accumulate in certain areas of the city. In bike sharing systems, for example, you have to employ someone to move the bikes back to where they need it. Or in Uber and Lyft, you have to come up with pricing schemes to incentivize people from going from undersupplied areas to oversupplied areas, or the other way around. When the vehicles are actually self-driving, you can coordinate them all centrally so that you can improve the availability throughout. Similar examples to this appear in other areas, whether it's to avoid congestion or to coordinate how these vehicles might charge and interact with the power system. So the problem statement is then the following. We want to find mathematical models. We want to come up with mathematical models that allow us to characterize how these systems will behave. Then, using these models, we want to synthesize control policies that allow us to control minute by minute how the whole fleet is performing so that it behaves like we want it to behave, whether it's from a societal or from an operational perspective. Then finally, we want to carry out case studies using real-world data and build applications in the real world so that we validate our research, but also so that we can inform stakeholders, whether it's public officials, academics, or industry practitioners. So what goes into an AMOD system? So let's consider this tiny toy city where you have a finite and fixed number of vehicles that are attending travel requests. A passenger arrives and he requests a ride. The system, so at this point this is very similar to what Uber or Lyft would do, the system assigns a vehicle, picks up the passenger and takes him to his destination. Once the passenger is dropped, however, this vehicle becomes available for other tasks. For example, you can move them to an area where it is needed to preemptively allocate the vehicle so that you're close to new demand. Or if it's low on battery, you can charge it. So let's talk about those concerns. What sort of concerns would an operator of an AMOD system have? So we talk about availability, essentially having a vehicle near to you whenever you want the vehicle. This can be either, if you think about from a station perspective, that there's a vehicle there, or if you think about it from a waiting time perspective, you want the vehicles to be within certain threshold, certain quality of service. But then you have other kind of concerns. For example, a municipality might be concerned that your system is causing too much congestion. So how do we leverage the fact that we have control over all these vehicles so that we avoid the congestion? And then finally, another concern that allows us to explore this topic is, if these vehicles are, on top of that, electric, then you have to be clever on when and where you charge. So we're going to use this set of problems as our canonical AMOD problems, but there might be a variety of different goals or different concerns that we will like to tackle. Now, aggravating these concerns is uncertainty. There's plenty of randomness, whether in the travel and the request process, so we don't really know when and where the next passenger arrives, although we have some notion. We don't necessarily know exactly how much time it's going to take to go from A to B, but we have some information. And then finally, there might be plenty of uncertainty in the charging process. So what we want is frameworks that allow us to characterize the system, taking into account these concerns, while accounting for uncertainty. So as Marco mentioned, this is a pretty hot topic right now, and there's plenty of work out there that's addressing this issue in one way or the other. We're going to separate this short literature review in two parts. One is the modeling side, and the other is the control. On the modeling side, there's a family of research which leverages mostly simulations. And the core of it is they assume a particular heuristic on how the system is going to behave, and then they run simulations on a city to see how that happened. And then from that inform whatever decision making they're trying to do. The issue, of course, is that by being heuristic-based, you're not leveraging you're not optimizing over the system. Instead, you just came up with a simple heuristic. The second problem is, if you want to understand how uncertainty is affecting this, you'll have to run a lot of simulations to start getting in the insights. A second family of approaches is what we call network flows. This has been quite popular in transportation throughout many years, in particular in the area of congestion. But it has also been used to address the topic that we're talking right now. In particular, several of my colleagues have worked on addressing these particular issues, these concerns that we just mentioned. However, they do not take into account uncertainty. They're deterministic. So the idea is, how do we move from this deterministic world to a stochastic one? And this is where queuing theoretical models play a role. There has been prior work in addressing mobility on demand systems using queuing theoretical approaches, but mostly towards addressing the issue of availability, not extending to other type of concerns. What we're going to look in this presentation is how to expand this family of queuing theoretical models so that we can address a vast variety of concerns. Now, on the control side, we're going to be a bit more modest. There has been plenty of work. We're going to address mostly the availability side. And in this case, there's two families of approaches, roughly. First, again, a set of heuristics, but in this case that were derived from first analyzing the system in steady state, and then coming up with a policy and applying it in real time. This performs quite well, and in general is close to be, or essentially the state of the art. However, by being formulated in a steady state perspective, you can't leverage forecasts. So this is quite a limitation. The second part is there's model predictive control, which is what we're going to essentially base the control side. However, current and existing model predictive approaches have the issue of either being limited in how it scales, so they have to be with small fleets of vehicles, 40 vehicles, 50 vehicles, or they have very limited modeling capacity. We have to make strong assumptions of how the system behaves. So the idea is to tackle both of these gaps. In the first part, I'm going to discuss some of the work we did on expanding these queuing theoretical models. So how do we capture all these concerns that we talked about? And on the second part of the talk, I'm going to talk about the model predictive control framework that we developed in the last several years. So together, this sums the majority of my PhD contribution during these years. And there has been other work that we won't mention throughout this talk, but you can ask me after the fact. So let's start on the first part, on the queuing theoretical models. We're going to make several assumptions to analyze the system. The first, to describe how the passenger arrival process happens, is that demand is time invariant. So the rate of arrival of passengers doesn't change with time. We justify this by making an observation. Here in this, on the bottom right plot, you have on the x-axis the time of the day, and the y-axis the number of pickups. And then you have a very thin line, somewhere around here, where that's your average trip duration. What I want to show is that your average trip duration is in a much smaller time scale than with which the rate of change of the number of requests happens. So we're going to assume that we're living in a world where the rate of pickups is sort of constant. The second assumption is what we call the passenger loss model. Essentially, when a passenger arrives and there's no nearby vehicle, the passenger leaves the system. So we're not implementing any sort of weighting. They just have a preference of how much they want to wait for a vehicle, and if it's not within this distance, they leave. Using those assumptions, we can abstract away that process into a single server queue, where the service rate is the sum of all the arrival rates for all the origin-destination pairs, and the throughput is the vehicle arrival rate. I want to highlight that this queue is from the perspective of the vehicles. So those are the actual queuing agents. So this is the passenger arrival process. The second part is the road travel process. Here, we're going to make a couple of assumptions and then convert it into queuing theoretical world again. The first assumption is that congestion starts at the nominal capacity. Again, we justify this by making the observation that when you are below the nominal capacity, speed is roughly constant. So this plot on the x-axis is the number of vehicles per kilometer, so the density, and the y-axis is the speed. And the cloud is a bunch of observations made in a particular highway. So what we're going to try to do is to just keep the number of vehicles in a road segment within the nominal capacity. The second big assumption is that for a given origin-destination pair, what we call a class, we have a pre-specified routing matrix. So going from one road to another road follows a particular distribution process, a particular distribution that is specified by what class this origin-destination is. Using this information, we can abstract the road segments using an infinite queue server, where we assume that regardless of how many vehicles are in the road, the average travel time is the same. We justify, again, this is fine because we are assuming they are within the nominal capacity. And in this case, the service rate is going to be the reciprocal of the travel time. So if we put everything together, we can transform our original AMOD system and abstract it away into a queuing network, in particular, a BCMP network, which allows us to set class-specific routes for each of the agents. So for example, in this case, we have the roads represented as infinite servers and the stations as single servers. And then we assume that there's a finite number of stations, which represent these two types of queues, and a fixed number of vehicles. This is important because by making a fixed number of vehicles, it means that this is a closed queuing network, and it's going to make some issues that we have to tackle now. What are these issues? The first issue is that we don't, because it's a closed queuing network, we can't directly compute the actual throughput. We can only get the relative throughput, which is the throughput of a queue, with respect to the other queue, so up to a constant. And the second one is that we can only, because of this, we can only get the relative utilization. So we have to go from those two to the metrics that we actually care, which are vehicle availability. What is the probability that when a passenger arrives, there is an available vehicle, and actual throughput. So what's the actual number of vehicles per minute or per unit time that are going through a road? And these are the formulas. And you might not know what this G of M is. It's a function of the number of vehicles that is quite expensive to compute. It's in closed form. It's a normalization constant for the probabilities, but it's quite expensive to compute. In particular, it's expensive because it grows. It's essentially adding up over all the possible combinations of states of the system. So if you have one vehicle here and three there, all of those permutations have to be added up. So how do we will tackle this in a bit. First, what is our goal? Our goal is to come up with a set of rebalancing policies such that we, keep the vehicle availabilities the same across the network, and we keep the traffic within the capacity. So more formally, we want to find rebalancing rates such that we minimize traffic, we have equal availabilities across all stations, have an expectation that all traffic is within the nominal capacity. Then this constraint essentially ensures that when you're going, that every vehicle that departs its origin reaches the destination, so every passenger gets served. And then this is a traffic balancing question, which essentially makes sure that vehicles that go into a node have to leave a node. And then the final two constraints is just ensuring that our routing matrix follows a probability distribution, a probability measure. And the second one is that we have no negative rebalancing rate, so we can't have negative rebalancing. As I mentioned, the main difficulty now is that this normalization constant is affecting two of our set of equations. First, our objective, and second, our expected traffic. So how do we get away from it? We rely on a key observation. If the availabilities in a network are equal across the network, then as the number of vehicles increases, the actual throughput approaches the relative throughput. This means that as m goes to infinity, as the number of vehicles goes to infinity, I can solve the previous problem as a linear program, which is it's easy to solve, or at least it can be solved very efficiently. The second key insight now is that because in this regime, in the large fleet regime, this network starts to behave as an open network, which means that now I can characterize the distribution of number of vehicles in a particular queue, infinite server, as a Poisson distribution, which means now that I can add to my previous problem setup a set of constraints that we call surrogate capacities, such that they guarantee that the number of vehicles at a particular road does not exceed the nominal capacity more than epsilon percent of the time. So we essentially solved this problem using this large fleet regime, and then tested it in a case study of Manhattan. So we took a subset of the roads in Manhattan, 1,000 roads. We took 50 stations, so we assumed there were 50 places where you can get picked up and drop off. We used a travel demand from New York. The Taxi Limousine Commission has a data set that's pretty rich, and we used rush hour from the morning of a day in March 2012. And then we placed the locations of these stations based on k-means clustering. And this is the sort of insights that this model can allow you. So we have on the top left corner a plot of fleet size versus availability. What this allows, for example, for an operator to answer is, okay, if I want to satisfy an availability of 90%, so that 90% of the time there's a vehicle for my passenger, I need around 2,400 vehicles. But obviously there's a trade-off. The more vehicles you have, the more idle vehicles you end up with. So the second plot shows you that it describes this trade-off. For example, at 3,500 vehicles, you end up having more vehicles that are idle, doing nothing, than actually serving customers. So this is the type of insights that this model enables. Now, we wanted to take advantage of that probabilistic constraint that we mentioned in the large fleet regime, and we tested two scenarios. One where we constrained the road capacity on expectation, and the second one where we want that the road capacity is exceeded at most 10% of the time. And what we see is on the left plot, the utilization of the road with the highest utilization. And what we see is that as I increase the size of the fleet, if we only constrain an expectation, you end up with almost 50% of the time exceeding the nominal capacity, which is not what we want. In contrast, when we constrain probabilistically, we have a much better bound. Now, we made an assumption at the beginning, which was that travel time, the average travel time is fixed, regardless on how many vehicles I have in the queue. But we wanted to see how far off were we. So we took the traffic flows of the city, and then we ran them through a traffic model, a Bureau of Public Roads traffic model. It's a widely spread traffic congestion model in transportation. And we wanted to see what is the increase of travel time for every OD pair, which is what we see in the second plot here, where the x-axis is the travel time with fixed average travel time, and then the percentage increase with the BPR model. And what we see is that at most, in the worst case, we have 8% increase. In particular, the worst cases are for the shortest travel times. So this sort of tells us that overall, our assumption is sort of mild. Now I talked about charging. So we want to touch all of these concerns. So now let's talk about how we include charging. We make the following assumption. We take the state of charge of the vehicles and we discretize it into B levels, such that we update now our classes into origin, destination, and state of charge, where state of charge is 1 to B levels. Like before, we are now assuming that our charging stations are modeled as an infinite server. So it doesn't matter how many vehicles are there. The time it takes to charge one level is independent from the number of vehicles. Now, there's a particular issue. We want to allow the model to give routes and rebalancing tasks conditioned on the charging level. We don't want to assign a passenger a vehicle that has very low charging. To allow this, we decouple the stations into two single server queues. We call this a double queue, where essentially, for them to arrive to the station, we assign them either to the passenger queue or to the rebalancing queue, where in this case, the rate at which the split happens is part of my decision. Now, as before, we were threatened by the normalization constant, but just as before, in the large fleet regime, this becomes a large linear program. In particular, it ends up looking like a network flow problem, where you have a repeat of the underlying road network at multiple levels. And like before, we can solve it as a linear program. So let's revisit that Manhattan case. In this case, we have 60 charge levels. We assume our cars are these tiny battery cars with 50-kilometer range, and that each station has a 75-kilowatt charger. To ensure that we prioritize passengers, we made their time 5 times more expensive than that of the empty vehicles. And this is sort of the things that this model can allow a practitioner to analyze. On the left side, you have the throughput for each of the charge levels of the station with the most passengers. What I want to highlight is how in the bottom charge levels, we're almost exclusively assigning those vehicles towards rebalancing tasks, regardless of the fact that we have a lot of demand in that station. Contrasted with the right plot, where we have the place with the most rebalancing tasks, where we essentially have rebalancing across most of the charge levels, but then even at the highest charge levels, we are reserving those vehicles for passenger trips. Now, one of the typical structural questions that an operator can ask is, okay, if I electrify my fleet, how many more vehicles would I need? And we can answer questions like this. Yes?
I didn't understand the difference between what changed between the left and the right plot?
So he's asking what is the difference between one plot and the other. So this is for the station with the highest passenger throughput.
Oh.
And this is with the station with the highest rebalancing throughput.
Okay.
So I wanted to showcase two extreme cases. So there are two different stations.
Okay.
Exactly. Two different stations with very different behavior. So as I was saying, we want to know how many more vehicles do I need to add to the fleet if they're going to all be electric? And the answer is, in this case, we have to increase the fleet size to keep the same availability, about 37%. And another question is, well, then how many of them do I expect at any given point in time that are charging? And this says about 10% of my fleet is going to be at any given point in time doing some charging tasks. So as I said, this is the modeling side. We proposed and tested a BCMP queuing network that allows the practitioner to include a variety of modeling aspects. We provide tools for, so yeah, if you want to distribute. We provide tools for how to analyze the system and also an optimization procedure to come up with optimal policies. Now, we touched on some of the concerns, the ones that we call the canonical concerns, but we can use the same framework for other topics that we are either working on or are in the pipeline. The first one is, for example, service equity. What happens if you have two types of vehicles and two types of customers where a subset of the customers require wheelchair? We're answering that question from a regulatory and from an operational perspective into how do we find both optimal policies from the operator side and good regulation that incentivize proper behavior from the companies. The second side that I think it's interesting to explore is when you have multiple competitors, how does that affect the system? How does it affect when you have a marketplace of autonomous vehicle providers? And I believe that this framework will allow us to answer this type of questions. So that concludes the modeling side. Now we move away from the super idealized world of steady state. And now we want to go into making decisions real time, minute by minute. In particular, we want to leverage forecasts.
Can I ask you a clarification? Yep. Why did you call that first segment the modeling side? Weren't you actually solving an LP to find rebalancing rates? And so
Correct. So why I call it the modeling side is because the main reason, I guess it could be called analysis, but the main motive is I want to be able to answer structural questions of the system as a whole versus making decisions there and then. Prior work has used the same models to synthesize control policies, but I wanted to make the distinction clear that this is more for answering like large-scale operational questions rather than the minute-by-minute decision making.
Okay.
So now we move to real-time control. The first thing I want to highlight is this is a plot of 21 days of travel demand in Hangzhou, China. Data given by Didi, the Chinese Uber. On the x-axis time of the day and the y-axis is the number of requests in a given 5-minute interval. And what I want to highlight is how it follows a sort of predictable pattern. We want to be able to exploit that pattern. But to do that, we need to
What's going on with the
New Year.
Huh? Okay.
New Year's Eve.
So it is an anomaly. Okay.
Yeah. Yeah, people are coming back quite late. Yeah, so we want to extend our model so that we can capture snapshots of the system throughout time. And to do that, we need to model the system a bit different. In particular, we can assume that we have two types of customers. One, the customer that's already here, that's waiting for a request. And the second one, customers that we expect to arrive within a planning horizon. Now, for the existing customers, we're going to ensure that we get a car for them ASAP. For the forecasted customers, however, we're going to say that if we don't have a customer there, a vehicle there, then it's fine. There's obviously a cost, but those customers simply disappear. So the forecasted customers follow the passenger loss model. In contrast to the previous, to the modeling side, now we're going to ignore congestion and the underlying road network. Instead, we're going to assume that trips simply follow the shortest path, and that this shortest path is independent of the decisions of the other cars. And as such, we're going to assume also that trip duration is deterministic. So as before, we're going to discretize the urban system into discrete areas. And then what we end up is with the time-augmented network flow model, where every node represents a particular area of the city at a respective time. And the arcs, so the arcs are such that the origin of the arc is the origin of a trip, and where the arc ends is the destination at the time when it would arrive. So now we have a sort of expanded graph. So let's look at an example of how would this look. We're looking at a snapshot at a particular time. We have a passenger at station 4 and a vehicle at station 3. We have forecasted demand from station 1 to 2 and from station 3 to 4 at time steps 2 and 3. And we want to come up with a policy for a vehicle. One policy could be this. We move the vehicle from station 3 to station 4, pick up the existing customer, take him to his place at station 3, and then satisfy that station 3, station 4 demand. Note that we've dropped the demand here with a penalty, but we've half. We can formalize this as follows. We want to minimize the amount of rebalancing and the customer waiting time and the amount of drop demand. So how many of our future customers are we reducing? Subject to customer flow, essentially conservation of customer flow. Essentially, every customer that appears in our model has to be accounted for, and we can't create and destroy. And conservation of vehicle flow. Essentially, every vehicle that enters a node has to leave that node. And then finally, this last constraint ensures that for the waiting customers, we always take them into account. Now, that addresses the optimization side. We have to include this within a whole control loop. And the control loop is as follows. We're going to follow a model predictive control framework where at a given point in time, we're going to observe the state. How many vehicles and how many customers do we have at each station? And then using that state and past historical data, we feed it to a forecasting model, which returns us a forecast of the demand within a planning horizon. We use then the forecasted demand and the current state to solve the previous optimization problem, the one we just mentioned. This returns to us a set of rebalancing tasks for the planning horizon, of which we're going to implement only the first part. And then we'll repeat the whole process. So we carried out a case study using this DD dataset. Essentially, we had 21 days of data, roughly about 330,000 trips per day. And we assume we had 5,000 self-driving vehicles. The data is such that there are 66 districts. And then we discretize time for our planning in 5-minute intervals. For our forecast, we trained the LSTM neural network, and then on the first 20 days. And then on the 21st day, we essentially took the data and replayed it in a simulation to see how it went. We tried 4 different algorithms. The first one, let's call it no rebalancing. Essentially what it does is, as customers arrive, they get served. But there's no pre-positioning. You don't move the vehicles ahead of time to address this new demand that's arriving. Then there's reactive, where essentially this is a state-of-the-art algorithm which was developed by Marco in 2012. And what it attempts to do is to keep the distribution of vehicles uniformly across the city. Then we have the last two, which is the model predictive control framework that I mentioned with the neural network. And the second one is the same framework, but with perfect information. So we feed it directly what's going to happen. So it's sort of an upper bound in performance. And what results is the following. On the x-axis, you have the time of the day during the simulation. And on the y-axis, we have the number of waiting customers. The first contrast is how much it improves from going from no rebalancing to the reactive algorithm. However, there is a huge increase in performance from going from the reactive to the MPC, where we leverage forecast. In particular, we reduce the customer waiting time by 90%. And in fact, when you compare it to the perfect information, there's apparently little room for further improvement. But you can always do better. In particular, in this approach, we left aside the uncertainty of our forecasts. This is the average demand for that same data set. And you can see that for certain occasions, the realization is very far from the average. So we want to take this into account, this uncertainty. How are we going to do that? We're going to assume that the passengers follow a particular underlying distribution that we don't know. And our new objective is to minimize the waiting time, the travel time, and the expected number of dropped demand based on the information from that distribution. The problem is we don't know that distribution. So what we're going to do is we're going to train a generative model, P hat, and then we're going to sample from that generative model case scenarios. And then we're going to approximate the cost function, the expected cost, by a Monte Carlo approximation. If we put it together, it looks like this. This is the same problem, but with the Monte Carlo approximation in it. Normally, this is called sample average approximation, where we are, again, optimizing for minimum weight, minimum travel time, and then the expected cost. There's an issue, though. We have a trade-off now between the number of scenarios that we sample and the optimality of our problem. In particular, this is aggravated because the problem as it is an integer programming problem, which can be very, very expensive to solve. There is a silver lining, however. The constraint that makes this an integer program is this. Essentially, accounting for those waiting customers makes this problem non-totally unimodular. So if I remove that constraint, it becomes totally unimodular. I can solve it as in linear programming and still get integral results. So that's what we're going to do. We're going to address the customers by a different algorithm, bipartite matching, for example, and then solve for the forecasting side, for the rebalancing side, with assuming there were no waiting customers. And in this case, the problem we just talked about becomes totally unimodular. The control loop updated looks like this. The new difference is that now when we forecast, we sample a finite number of scenarios, and that the system state first goes through the bipartite matching. Then we update the system state based on the results of our bipartite matching, and then we feed that to our stochastic for sample average approximation algorithm. Again, we just implement the first part of our results and then move on and then repeat. Yeah.
Quick question. Go back to that. So the bipartite matching is addressing the customers that are waiting right now, and then the other one's doing the forecast forward.
Correct. So we're separating addressing the future demand and the current demand.
Current demand.
Exactly. Which, in all fairness, is essentially what happens currently, because in current systems, you rarely have waiting customers anyway. They get either matched quickly or they switch to some other application. So I think it's a fair way to address the issue. So we're going to revisit that DD case study, now using the stochastic approach. For capturing the forecast uncertainty, we're going to do the following. We're going to train the same neural network using dropout. And then we're going to sample k means from that neural network using dropout, which is a way of approximating the uncertainty on my neural network. And then each of these means essentially describes a Poisson distribution. And we're going to sample from each of those Poisson distributions once. That gives us k scenarios with which to optimize over. The results are yet another significant improvement. Here we see on the x-axis, again, time. Y-axis is on top waiting customers. In the middle, the number of rebalancing vehicles. And at the bottom, the standard deviation of demand in a particular time. What I want to highlight first is that the main improvement happens in the areas where we have highest uncertainty, as we would like to see. The second is, interestingly, we have a lot of rebalancing happening at the beginning of the day, probably preparing for that outlier of New Year's Eve. We can now resume the whole story a bit more. We went from no rebalancing to dropping by half the waiting time when we implemented reactive. Then we dropped 90% by using the forecasted approach, the MPC approach. And then from that MPC approach, we dropped another 62% by including stochasticity. There is a 60% gap left with perfect information, which at least seems quite promising. Promising enough to try it out in the real world. Which brings us to the final stretch of this talk, we took these algorithms, these MPC algorithms, and we wrapped them up to deploy them in a car sharing application. These vehicles are by no means autonomous. They are from Toyota, so this is a collaboration with Toyota Research Institute, and they have what they call harmonious mobility, which is a car sharing system where you can take a vehicle from one point to another and leave it there. It has like one-way car sharing. Currently, like everywhere else, they have issues of vehicle and parking availability, and they employ people to move the vehicles around. So our goal is to come up with an automated system that tells the employees what to do and which vehicles to move where and when. So just to describe a little bit the system, this is the stations of the locations of the stations throughout Toyota City, and then this is the departing trips in the morning and where they are arriving. And I just want to highlight the imbalance. Essentially, the vehicles are mostly leaving the center of the city and arriving Toyota headquarters. So this is sort of problems we're trying to address. And what we built was we took the same algorithm, we adjusted to account for the new system that we're actually observing, and we wrap it up with a back-end system that talks to the Toyota servers and talks to two particular applications, a front end that an operator in a desk can use, and a mobile application that the rebalancers carry around for doing these tasks. We use this application both to validate and to improve their system, but also to improve our algorithms. We went through a whole year of feedback loop where we use the OUI, which is the operator user interface, to get feedback from them. The first part, the back end, the core, the brain of the system, had to make some adjustments on the original algorithm. In particular, we make two adjustments. One, we added new penalties on vehicle and parking availability. And second, we added an operational cost, which reflects the willingness or lack thereof of the drivers to walk, or the balance of walking from one place to another. In addition, we had to add two new constraints. One is driver continuity, so our model can create and destroy drivers. And the second one is a particular parking constraint. This system, as it works right now, is such that when you reserve a vehicle, you reserve not only the vehicle, but also the end parking station, parking lot. So at any given point in time, a vehicle is occupying also a parking lot. So we added that there. And now I want to show you a little bit of how the application looks like. So the idea here is for the operator to run what-if scenarios, to understand what the system is doing behind, and to observe how the system is, what the state of the system is. So here, he added two rebalancers in station 22. He asked the backend, what should we do now? And it returns two set of tasks with a finite horizon for our planning. In particular, in this case, it says, one of them should walk from station 22 to 49, and then take a vehicle from 49 to 44. The other application, the multi-user application, is the one that's used by our friends that are in the field. So here on the right, we see, on the left, we see Makoto, who just finished a rebalancing trip. He goes into his application, and he asks for a new task, given where he is, where his peers are, and what the state of the system is. And he gets a new request, essentially, walk from station 7 to station 16. And then take the vehicle from 16 to, I didn't see the other vehicle. The other station. But essentially, you get the point. They're getting new tasks, finishing them, and we update in the backend. So we had a long back and forth of sharpening this application. And last December, we had a sort of a sprint where we worked for them for over 10 days, culminating into a couple of days where we let them unsupervised to try out this application. And what we see is this is one of the days. In particular, we see some of his tasks, the tasks that he carried out over 1 hour and a half. So essentially moving a vehicle in the center of the city, coming down, making some adjustments, and then moving on. When we compare with the rest of the year, we see some improvement. What we have here on the right, so we define coverage as the number of, in the case, for example, of vehicles. Vehicle coverage is the fraction of stations that have at least one vehicle, and the similar concept for parking. And if we plot a box plot of all the change in coverage for that particular time segment over the entire year, we see that the tasks that we issued and that were carried out in that period of time are essentially outliers. So we're doing much better than whatever they're doing before. At least in this particular case, we're doing much better. This is far from a, exhaustive study, but this is very promising. And we are in ongoing talks with Toyota to continue to develop this system and deploy it in further cities. So as a summary, we started with a model predictive control framework that then we expanded by adding stochastic features to it. And then finally, we deploy it in a real-world application. So I promised to you to go from modeling to control and then to hit the real world. The next steps are to carry the same, this same sort of deployment, but in a more widespread deployment. So what if they use it for longer time and exclusively as their modes of operation? The second next step in this particular area is how do we come up with forecasting models that capture the request uncertainty, but also that allow us to sample the scenarios that best inform our optimization problem. More futuristically, we want to carry out social studies for how this whole AMOD thing is going to impact them. We talked a little bit about the equity side, but there might be other aspects. For example, how's it going to affect land value? Another is, well, with all of this information, as we develop more and more tools, we can move from optimizing the mobility of the vehicles or how we control the vehicles to how can we incentivize humans to move in a way that is socially optimal, in particular as it pertains to when you have multiple modes of transportation. And then finally, there is a sort of coupling between the features of a self-driving vehicle and the system in which it operates. Coming up with methods for optimizing both jointly is a particular area of interest. So that's the conclusion of this talk. As I said, I talked about the queuing side, modeling and analysis of the systems, the model predictive side, where we can control them minute by minute, and then finally we tried out this in the real world. This was sponsored by Toyota Research Institute and by the National Science Foundation, so I would like to thank them. And I would like to thank all of you for being here. And, well, thank you for the committee, Ram, Rishi, Mac, Rebecca. Special thanks to Marco for all the lessons, particularly the technical and the political. Special thanks to all my collaborators, Federico, Matt, Steve, Mauro, Ryder, Rick, Kirill, the folks at Toyota, Masa and Steve. Thank you all for ASL, which is the majority of you. Special thanks to the folks at Copa Cafe who kept me caffeinated, Nadia and Gemma. Thanks to my friends. It's been a lot of fun. And then finally, thanks to my family and my girlfriend for, well, all the support. Well, with that, I finish. Open myself to questions. Thank you. Mauro.
What is the thing you're mostly proud of?
Mostly proud of?
Yes,
The Toyota project was very, it's very different to just try it in your computer to going there and hitting the real world. I thought that was, I'm pretty proud of that. However mild the results are for the moment. Sarah?
Do you find a lot of variety in ride sharing, like how these issues vary geographically from country to country?
So the question is, do the issues vary a lot geographically from country to country? I think the underlying problem does not. I can speak from the 3 data sets that I've been looking at, and those are the Hangzhou, Manhattan, and the Toyota City one. the DD one and the Manhattan one look very similar, whereas the Toyota one, being a car sharing, has a very different demand pattern. Much lower demand and very much unimodular in the sense that there's just certain routes that are taking versus all over the place. Karen?
I guess which part was more challenging, the modeling side or the control side? And also, are there any like model-free approaches to this problem?
Great question. So the questions are, what was more challenging, the modeling or the control side? And the second question is, are there any model-free? On the first question, I think the modeling side is a bit more challenging, in particular because you're trying to come up, you want to make statements that are principled versus things that just work. And that made it difficult. In particular, sometimes you have to twist yourself a little bit to fit a particular framework. As for model-free, there have been some attempts to use model-free reinforcement learning. I think the results thus far in that area have been very mild when compared to model-based. But I can see some future in a combination of both, where you use model-free to inform a particular controller. Max?
Maybe if you think 5 years further, so models are getting even bigger. Now we are including uncertainty. We're still focusing on certain OD pairs. So assume we get more players, even more granular models. What is your view of the system working in 5 years? Is it still one integrated algorithm solving all parts of the puzzle? Or is it more a layered algorithm solving pooling by matching routing separately from the dispatching? So what is your view on that?
It's a fantastic question. So the question is, how do you, 5 years from now, how is this going to look like? How do you layer out, how do you increase in scale and features? And to that end, I think the future, or the next steps is in being able to compartmentalize, I don't know how to say that, to box separately the different features or issues that you want to address. Maybe just like we did right now for addressing matching and rebalancing separately, you want to do the same for, I don't know, for charging, and then you want to come up with models at scale for each of those. But then maybe have a particular model that connects them, all of them. So I think there might be ways to communicating via some of these variables to the independent models and the independent compartments. Yep.
Great talk. I'm
Thank
curious
you.
if from the data you looked at, you got a sense of what's the reasonable wait time? Like how much time are customers willing to wait before they'll drop in the settings?
Good question. So the honest answer is I don't think you can say anything from the data we have, because both the Manhattan and the DD one are essentially time-stamped at the time they got picked up versus at the time that they were requested. Actually, no, that's true. That's true for both.
On the slides, I think you have a 37% increase of fleet size if you want to electrify all of them.
Yes.
Was that looking at particular battery size and charging rate and station layout, or did you experiment with those three as well?
So that was just with the assumptions that I presented first. So I think some interesting would be to, okay, as you vary battery size, how does this look like, or if the station chargers. And I think that plays hand in hand to the co-design. So for example, you have this model that tells you, okay, how many vehicles you need to keep that level of service, but then you also are trying to spec out how much battery do you want in your vehicle. So I think that's an interesting next step on that area.
Any more questions? All right, so with that, we conclude the open.
All right. Thank you, everyone. And if you're around and want to say hi, we're going to have a barbecue after I finish with the closed sessions, and you're all more than invited. Thank you. Yeah, where we had the barbecue last time.
Yes, yeah. Yeah. Victor.